All right, today we're jumping into a really big question, maybe one of the biggest in modern engineering. How do you actually prove a self-driving car is safe? And what's fascinating is that the answer isn't a simple number. It's an argument. So let's kick things off with a question that might seem simple at first. I want you to imagine a self-driving car that's, well, perfect. No bugs, no glitches, it's doing exactly what its designers told it to do. Can that car still get into an accident? The answer? Yep, absolutely. And that one word is at the very heart of the entire challenge of autonomous vehicle safety. It's not about preventing every single accident, because, as we're about to see, that's just not possible. Okay, so first things first, we have to tear down this idea of perfection. Because before we can even begin to talk about what is achievable, we need to get our heads around why a totally 100% safe, zero-risk car is, well, it's a fantasy. And here's the bottom line. We're talking about the physical world here, right? Governed by the laws of physics, not some perfect simulation. And out here, any object that's moving has risk, period. And this little equation right here, this is why. You see, this is the formula for kinetic energy, and it's a law you just can't argue with. As long as your car has mass, that's the m, and it's moving at any speed, that's the v, it has energy. And that energy, well, it can do damage in a crash. It means the severity of a potential accident can never, ever be zero unless the car is completely stopped. So physics itself is telling us that perfection is off the table. So this leftover risk, the stuff you just can't get rid of, engineers have a name for it: residual risk. It's what remains after you've implemented all your safety measures. Think about it. A car drives in what's called an open world. You've got unpredictable weather, other drivers doing crazy things. You just can't control everything. So the big takeaway here is that every single self-driving car is basically born with some level of risk already built in. Okay, so if we can't get risk down to zero, what's the next step? What do we do? Well, we have to manage it. And that brings us to maybe the single most important part of this whole process: figuring out exactly where we draw that line in the sand. This right here, this is the question. It's not just for the engineers in a lab. It's for regulators and really for all of us as a society. And it goes way beyond the technical stuff. It's a deeply philosophical, even ethical question. I mean, what does safe enough really mean? So, in the world of engineering, they don't leave this to chance. They formalize the answer in something called acceptance criteria. Honestly, the best way to think about it is like a contract. It's a clear, defined target that basically says, look, if our system's risk level is below this line, we've done our job. We can stop this phase of testing and move on. Without that stopping rule, you'd just be stuck testing forever, right? You'd never ship anything. So how on earth do you decide where to draw that line? Well, the good news is engineers aren't just making it up. They're standing on the shoulders of giants from other super high-stakes fields. Think aviation, think nuclear power. And all that work has led to four main ways of thinking about this, four big philosophies for defining safe enough. And these are the four big pillars that engineers use to build their safety argument. You've got GAMB, which is good as the average man benchmark. Then there's positive risk balance, or PRB. You've got ALARP, which stands for as low as reasonably practicable. And finally, or minimum endogenous mortality. Now, I know they sound a little intimidating, but trust me, the idea behind each one is actually pretty clear and powerful. Okay, this table lays it all out perfectly. Let's just walk through it. GAMB, good as the average man, is pretty straightforward. It just asks, is this thing better than a typical human driver? Next up, positive risk balance, or PRB, zooms out a bit. It asks, does this technology make our society as a whole safer? ALARP, as low as reasonably practicable, is kind of the engineer's reality check. It's asking, look, did we do everything we reasonably could have done? And then there's MMEM. This one's the ultimate safety net. It asks, is the risk from this new tech way, way lower than the everyday background risk of just being alive? Now, here's the really important part. In the real world, you don't just pick one of these and call it a day. The standard practice is to actually weave them all together to create a really robust argument. So you might, for example, use that better than a human idea from Gamma as your main goal. Then you use PRB's logic about societal benefit to justify putting the cars on the road in the first place. And all the while, you're using ALARP to make sure you're using your resources wisely. It's like building a defense with multiple layers. All right, so those philosophies give us the why, the big picture thinking. But engineers, they live in the world of the what. They need hard numbers, specific rules they can actually build to and test against. So let's take a look at how all this high-level philosophy gets translated into the nitty-gritty, day-to-day work of making a car safe. Okay, so this number, 4.0 meters per second squared, it might not look like much, right? But it is a perfect example of what we're talking about. This comes directly from a regulation called R157, which was developed by a UN group that sets vehicle standards. And what it is? It's the minimum braking force required for certain automated steering systems. And just like that, a fuzzy philosophical goal like the car should be able to stop safely becomes a concrete, measurable pass-or-fail test. It's either braking at 4.0 meters per second squared, or it isn't. Simple as that. So that leads to another question. How do you even define what a good driver is in a way a computer can understand? Well, on one hand, you've got these really formal mathematical models. A famous one is Mobileye's RSS, or Responsibility Sensitive Safety. It basically takes concepts like maintaining a safe distance and turns them into rock-solid mathematical equations. And on the other hand, you have this idea of a competent and careful driver. It's like a profile of an ideal human driver, someone who follows the rules, pays attention, isn't aggressive. The goal for the self-driving system is to be better than that person. And again, you use math to pin down exactly what careful and competent mean in the real world. And then, of course, there's the power of the market. Getting a 5-star safety rating from a group like Euro NCAP, that's a massive deal for any car maker. It sells cars. So what happens is the very specific tests they run, like a kid suddenly running out from behind a parked car, those scenarios become the de facto targets that engineering teams are laser focused on passing. Okay, so we've got our philosophy, we've got our rules, we've got our test targets. How do you pull all of this together into the final proof that the car is safe? This is the final step, and it's called building the safety case. A safety case is basically a formal, structured argument, and it results in 3 really crucial documents. First up is the hazards list. This is literally the engineers brainstorming every single thing that could possibly go wrong at the vehicle level. Second, you take that list and you evaluate each one. How bad would it be if this happened, and how likely is it to happen? And finally, number 3, you formally declare your acceptance criteria. This is where you write down in black and white your measurable, provable definition of safe enough. So if you take away one thing, let it be this. Safety isn't a feature. It's not something you just install in a car and then check a box. It is a continuous process of argumentation and proof. It's a case that you have to build, test, and defend with real-world data, starting from the first design sketch all the way through the entire time that car is out on the road. And that, of course, leaves us with one last thought to chew on. If safety really is a journey and not some final destination, well, then what does the road ahead actually look like? It means the standards, the tests, our whole idea of safe enough, it's all going to keep changing and evolving. This debate, it's really just getting started.